Right. So this is just a recap video of what we've done relating to the topic of completing the square. Now, actually, to be honest with you, I should probably relabel this and just call it quadratic graphs because this links. Completing the square is to do with quadratic graphs. But let's just first. Okay, so let's start from the beginning. When we first introduced, when we were first introduced to quadratic equations, we saw this equation here. Okay, y equals ax squared plus bx plus c. So if we look at this equation here, so this is our first format of the equation: x squared minus 10x plus 21. So the c value is the 21. So I can colour that green. Well, I can try and colour it green. Let's try that again. And the b is minus 10, not just 10, because this is plus bx over here, which is the same as plus negative 10x. So it's the same as take away 10x. A would be 1 in this case. So we've identified the values A, B, and C down here. Okay. The next, when we have to solve quadratics as if ax squared plus bx plus c is equal to 0, we have to rearrange it to this format. And what this does, well, I'll link this to the graphs in a moment. So we've been familiar with this format as well. And all it is rearranging the equation. But the way you rearrange equations, the way you rearrange quadratic equations is very different to the way you rearrange linear equations. When I say quadratic, I mean when the power of x can be up to 2. Okay, so this is the other format. When we did this, we know how to factorize quadratics. We also know how to factorize quadratics when a is not 1. But when a is 1, we're just looking for a number where f plus g, these numbers here, is equal to b. In other words, two numbers that add together to give minus 10 in this example, and the same two numbers times to give c. So what two numbers add to give negative 10 and times to give 21? The two numbers are negative 3 and negative 7. When you add these two numbers together, they give you minus 10, and when you times them, they give 21. So those are the two numbers. And you can expand this back out to prove that that's the case, but we're not going to do that. We're familiar with all this. So that's the second format. The third format, getting something into the third format, is called completing the square. This is the third format here. And the format is over here. This is the version of, we've done it, but we haven't. But I want to explain how to do it as well now. So if these, so basically you can analyze this and connect and compare it with this format, this third format, and we can see that D must be negative 5 and E is negative 4. Okay, so those are the three formats of the equation. What does each one tell us? Well, we've got basically the A just really just tells us how squashed the graph is. So you might get, so you got a curve like this. You could have a curve that's more squashed like that, or even more squashed like this. And this might be A is equal to 3, and this might be A is equal to 1, right? And yeah, that could be A equals 2, of course. And then you could have A equals 0.5 and get even more stretched out. So that's just what that does. The C is the y-intercept. And if you think about it, the y-intercept is when x is equal to 0. So if x is equal to 0, what would y be when x is equal to 0? Well, looking at our equation here, x squared would be 0 squared. Minus 10 times 0 would be obviously just 0. And then it's plus 21. So it's just going to be the C. Okay? So just think about it. If x is 0, then y would just be equal to c. Right, so that c is the y-intercept. Sorry, the x in... c is the y-intercept when x equals 0. F and G, they are the x-intercepts, because the x-intercept is not when x equals 0, it is when y equals 0. So, so if y is equal to 0, it's not actually the quite the x-intercept. Let's just show you what I mean. If I take the example that we've got up here, in fact, we did it here. So when y equals 0, x minus 3 is equal to 0, or possibly x minus 7 is equal to 0. Rearranging that, we would say, therefore, x is equal to 3, or x is equal to 7. So actually, it's going to be the negative of f and g. So maybe I can go back over here, and I can say not the negative x-intercepts. Okay, the negative of those x-intercepts. The last one, which is what we're going to be talking about in a moment, is the completing the square. When you get it into that format of completing the square, this one up here, the D and the E are the points, are the minimum point, otherwise known as the turning point. So back to these curves up here, it's the minimum point. It's called the turning point because before it's going down, and after that point it's going up. So we can say it turned, it changed direction, all right, at that point. So we call that the turning point. The D, the one inside the bracket, is the x-coordinate, and the E is the y-coordinate. Now actually, it's not just the y-coordinate again, but it's one of them is the negative, I think. So we need to confirm that in a moment. Let's just have a quick look at this. So the D is the x-coordinate, but the E is the negative of the y-coordinate. So let's just edit that down here. So the E is the negative of the y-coordinate. Okay. So I'll just move this up here. The negative of the y-coordinate. Okay. So that's, now we know what they'll do, what they'll tell us about the graphs. Now, what about the how do we complete the square? Well, the shortcut is there's a relationship between D and the other letters, and it's just this, and the relationship between E and the other letters is this. And so we can work all this out, and we can see that it does in fact work. There's D. If you put in the values for A and B, we do in fact get what D is, and if we put in the values for what E is, we do get that as well. So these are both correct. But we want to understand it at a greater level. Let's imagine that we had our standard equation, but this is actually, we're going to start off a bit simpler. We're going to forget about A again. So we're going to say A is 1, all right? Let's use the right colors. I used A was purple before. So this is only, I'm not going to go into where A is greater than 1 because this is already super difficult. So we're going to stick with this to start off with for a while, really. So basically ax squared, but A is 1, so it's just x squared. So we take just part of the equation, x squared plus bx, and we forget about the c to start off with. And we imagine that this is an area. And so imagine a rectangle where the dimensions of the rectangle would be x plus b multiplied by x. And you chop it in half and you get a rectangle, a square here, and a little rectangle here. And so the area of this square is going to be just x times x, which is x squared, and the area of this one is going to be b times x, which is bx. So the area will in fact be x squared plus bx. So next thing that we do is we take this orange rectangle up here and we split it down the middle. So we have So we can take, let's get 2 of these. So we split it in half, like that. Oops, okay. Yeah. And the dimensions, therefore, will be not b times x, but b, a half b multiplied by x, and another half b multiplied by x. Now, the reason why we want to do that is because we're going to move one of them down here. And now the dimensions it's nearly a square, isn't it? It's nearly a square apart from this little bit up here, because this is going to be x plus half b. I think I might make it get a thinner pen actually. No. So the height of this nearly a square is x plus half b. So rotate that a little bit. Multiplied by x plus half b. So that would be a square, but it's not quite complete. This is why we call it completing the square. Because what do we need to add to complete the square? Well, this dotted square in the corner of the square, the dimensions would be half b multiplied by half b. So that's what we would need to complete the square. So the area of this, remember originally it came from part of our equation x squared plus bx. The area of the entire shape would be the area of this full square minus the area of the missing part of the square, and that therefore would be equal to x squared plus bx. So what would x squared plus bx plus c equal to? Well, it would be equal to all of this left-hand side plus the c, which is what we've got down here. I'm just going to move these because it's overlapping a little bit. So, so this bit on the right-hand side is we're comparing it over there. I'm just going to get the other copy of the initial version as well. And just to recap, the bit on the left is the first format of the equation. I've forgotten the 1. Oh, not what I wanted to do. Okay. So that's the first format of the equation, which we can, I might also shrink. So that's over there. And so basically comparing this to that now, we can see that the D is this bit here. I'm going to just color code that as purple. Not quite right. I'm just going to pause this while I do that. And you can see that when I added E, essentially, I've sort of added all of that. So I could probably just put that in brackets, move it all along over here, and we can say that I've added negative. So you can see that this is the same as E. So so therefore we could rewrite it as this and rearrange it if we like. Now because Y didn't involve A, then we haven't really seen how, if A wasn't 1, how it would be involved. I haven't got that far with it, but if we have a look at the equations that they gave us, then it's you put them in here, and essentially we get the same thing. Okay. Okay, so it's a very, very difficult topic. So what we need really is practice. Okay, so that's what we're going to do today.